Alright, so this video is going to go over some of the things that we can look at based on the suggestions from StellarX for QR2, the upcoming round. I wanted to get this video out a little bit earlier, but unfortunately things got delayed, but this should be hitting the internet at least a day or two before the actual scenario begins, and this is just going over the broad strokes of the materials, so hopefully you're watching it before your competition time, but hey, if it's helpful, that sounds great. Of the things that we want to take a look at, and we'll go through in order and talk a little bit about each of those. If you're a veteran team, teams that have done this for a little while, hopefully a number of these things are going to be familiar to you. But especially if you're a newer team or someone with less experience, then this will hopefully give you a way of approaching and understanding some of the stuff that we want to get ready for. Okay. The main things that we're going to look over are based off of the email that we received that said, hey, these were the things that were suggested to take a look at. One of them is access times, and that's something that was important in some of the previous rounds, actually pulling up the access time between various targets. And I do say targets, plural, because sometimes you have to balance getting information from one site and then relaying that information to another site. While we're not going to do a deep dive into that, I will show you some of the things that might help you do a more complex analysis with something called CSVs. Those are comma-separated variables or values is the file format. I'll show you how to get those from STK and how to bring them into Sheets and a little bit of how to work with them. I'm also going to show you something called a gaps report, which can be useful if you're not going to do necessarily the full CSV approach, which can be time consuming and difficult. The gap report can give you some very useful information at a glance, and it's not necessarily obvious in how to find it. Now, beyond the access times, which is something that we've needed to use in the past, something that's probably relatively new, at least specific for QR2, is going to be our attitude control systems, ACS. In particular, we suspect that there may be parts where you'll have to supply enough fuel for them. So we're going to talk about what they are broadly, kind of imagining what they do, and what we'll need to do most likely in a challenge related to choosing an ACS system. We're also going to talk about power systems. That results in what we would normally refer to as power budgeting, where you're going to have to keep track of energy coming in, usually from the solar panels, storing that energy in battery, and making certain that you've got enough so that your satellite always has enough power so that it can run its systems. We're also going to talk about some of the limitations of battery technology, battery cycles and their lifetime, something that could come into play in choosing a good battery for your mission. We're also going to talk a little bit about thermal management, specifically about the importance of radiators, and something that's counterintuitive, that while space is very cold, our biggest worry is that we don't accidentally cook our satellite. And then finally, the last of the suggestions on there was also taking a look briefly at propulsion. I don't know exactly fully what that's setting us up for, but it may also involve having enough fuel so that the satellite or spacecraft can engage in maneuvers or change from one orbit to another. We're going to talk about each of those in turn, but this is what we'll take a look at in this video. So going forward, access times. Okay, key ideas. A lot of what you're going to end up doing with QR2 is usually you've got several targets, you're getting information from one target, pulling it up to the satellite, saving it on a hard drive or a data recorder, and then retransmitting that down to a ground site. You're going to have to balance out and do what we call a data budget. You're going to have to see how much data is coming in, how quickly and when. You're going to need to see how much storage space you need to try and hold on to it. And then you're also going to need to see how quickly you can offload that data down to a target site. So key ideas on that are the access time to a target that adds data onto the drive, and it'll do that usually at a certain rate, sometimes instantaneously, confusingly, but sometimes it'll be based on the scanner or sensor you have. The total space on your hard drive, so you have enough room to hold on to as much of the data as possible. If your hard drive fills up, then you lose data. You can't save anything to it. And the transmission rate to your destination, how you can offload data, remove it from the drive, and safely secure it at your target, which usually results in you getting points. Now, it isn't just any contact time with the destination. You have to make certain that there are effective minutes worth of data, or data that's useful, going down to that destination. And as a result, timing is very, very important with these. We'll talk briefly about some of the things that I can recommend on it, but if you want to be exceedingly thorough in this, exporting this information, these access times, as CSVs, And working with them in sheets or a spreadsheet, say Excel, can be a great way to actually be able to tell exactly what you do and do not have. In fact, many of the things that we're going to see in this presentation, it's great to actually export those files as a CSV so that you can tell more than just, hey, it looks like it's going to work. You can actually solve it completely, at least in most cases. If you're working with patterns, which is a way of cutting down the amount of work, but being a little iffy on the outcome, because with patterns, so long as the pattern holds, you should be good, but if you're cutting it very close, sometimes you might have a little bit more or less communication time that might burn you a little bit with the patterns. But check for both contact times and gaps with the gap report. And that is going to lead us to the first thing that we're going to take a look at. I'm going to go over to a scenario that I just have. This is one of the ISAT ones. This is ISAT 1, QR1 series, C series, and number 2, the second scenario, and this is just the default that I brought up. It's Sentinels Blind. I basically brought up a pre-existing scenario that I could pull information from. While I'm not going to go into the details of what the actual goal on this particular scenario is, and we only have one actual destination, or target that we're interested in, which is North Sentinel Island, and we're not interested in necessarily getting that data back to the ground. The biggest thing that I wanted to do is I wanted to show you bringing up the access times. I'm going to go to my satellite, and I'm going to right-click on it and go to the access times, like usual. Hopefully you're very familiar with this. And we're going to get the access times between it and our target at North Sentinel Island. I can click Compute, and I can click Access Report. Right here, we have the often used access report where it shows the timestamp of every time my satellite has contact with North Sentinel Island, in other words, that it can see it line of sight, and the duration. So I can see here in this particular scenario, my first access happens on 7th of June 2020 and lasts for about a little under 9 minutes. My next one is 13.5 minutes. My next one after that is about 12 minutes, then 10, then 10, then 12. You can see that there's kind of a pattern here, but every so often we're going to see some weird glitches in this, where a bunch of these are on the 7th of June, and then I've got one of them where there's only contact for about 2 minutes, and then it goes back to about 13, 13, 11, 10. There's a lot of patterns here, but like I said, if you're going off of patterns, you're going to have issues where sometimes the pattern breaks. And part of that, if you actually go through and watch this, you can see that in that 2-minute period, it's right where the satellite kind of sees it, but then the Earth turns enough where it goes out of contact. And so you're going to have a lot of cyclical things. In fact, they're usually not even random. We can see I've got 9 minutes. That probably would be longer, except it's at the beginning of the scenario, it looks like. But I've got like 13, 10, 10, about a bunch of 10s, and then all of a sudden there's a 2. I keep going down, there's a bunch of 10s, and then eventually I have... I go down a bit more, and on the 12th of June, it happens again, where we get about 1.5 minutes. I could go through, and in a longer scenario, I can try and look for these patterns and see, okay, there are parts where it breaks, and see if I can figure out how many cycles until that happens. I don't want to get too stuck in the weeds on this, but I do want to point that out. When you see something that looks like an anomaly, if you keep going long enough, you'll see that it probably happens again a little ways down the road. But that may depend on the nature of your scenario and how things are set up. Now that being said, getting back on to point, we could see here that if I knew how much data I was actually pulling for every minute of contact, I could say, hey, if I get 2 gigabytes every minute of scanning or looking at North Sentinel Island with my satellite, and I'm getting about 10 minutes on average, I could say every time I loop around and see the island, I'm getting about 20 gigabytes worth of data. And as a result, I could see how big of a hard drive I need to do. And I could do something similar with wherever I'm offloading that data and try and see, okay, well, I'm adding 20 gigabytes on one side. I'm going to need at least a hard drive big enough for 20 gigabytes. And I'm going to need to choose a transmitter that can hopefully get 20 gigabytes offloaded. Now that's just me glancing at this. I can also come down to the bottom, and at the bottom I have the maximum duration, the minimum duration, and the mean duration. Mean is the average. And so on the average, instead of 10 minutes, I could say, hey, the average contact is actually 11.5 minutes. And so if that's 2 gigabytes per, then that would be 23 gigabytes. Now, if I was assuming the 20 gigabytes, maybe I'd get a 22 gigabyte hard drive, and I'd be dropping a gigabyte on average every time I went through. Whereas if I could get a slightly larger hard drive, maybe I'd be able to keep those. The other thing to keep in mind is, remember, this is the average, so half of my contacts will be this or less, but half of them will actually be greater than this. And so as a result, maybe I want to go with the maximum, but I don't know how many of those that would actually bring in. There are things that you want to think about. But I will also tell you this. Okay, the other reason that we've come here is not only am I interested in how often I'm in contact with it, it also helps to know how often I'm not in contact with it, so I know how much space I have in between them. There are a few things that I want to show you on this. First off is exporting a CSV, which was one of the big things that I had mentioned. Okay, up here we have an old school disk where that's save as text, but right next to it we've got a small disk in front of what is actually the Excel logo, and it says save as .csv. So I click on that, and it brings up a folder that I'm on, but I'm going to go to my desktop, and I came prepared. I made a folder called QR2 prep, and it will automatically title this named after the access report. Satellite ISAT to target North Sentinel Island access. So I'm going to go ahead and click save on that. Okay, great. So I've got that aspect. Now I'm going to go over to a spreadsheet in Sheets. So here in Sheets, I've set up a file called StellarX10 QR2 prep, and I want to bring that data in. Sheets is actually really good at this. If you try and do this with Excel, you usually have to do a couple more clicks and steps. Sheets is actually really good at working with the CSVs, at least for importing them. What you want to do is you want to go to File, go down to Import, and we're going to go to Upload. Do Browse, and then find the folder. It helps if you keep track of where it is. Don't just click Save when it says Export it, because then you're going to have to go looking for it. Make a folder that is easy to work with and save your files there so that you can go to QR2 prep, and I can now import this. It gives me some options: create new sheet, a couple of other things. I'm going to do replace current spreadsheet, which is certainly fine. It's warning me, hey, you're going to overwrite everything that's there. And I'm like, yeah, that sounds fine. Detect automatically and convert text to numbers, dates, and formulas. And I'm going to click import data. It'll take a moment, but then now it's actually taken that entire access report, which in STK is nice and easy to look at here, but I can't do any work on it. I'd have to write down all those numbers. I now have it where I'm sitting here looking right at it. We've got the duration in here. I'm going to show you some basics on how to do the math. The duration, I'm going to show you something. So here is our duration. And I'm going to mark this in days. Okay, so I'm going to hit equals to do some math. And I'm going to take the stop time. I'm just going to click on it. And I'm going to hit minus and the start time and hit enter. Now it gives me a weird number that says 0.006086, etc. That's actually the stop time minus the start time, but it's in days. I want it in minutes, which I'm going to call duration minutes. I can easily take that, equals, I'm going to take this value in days, and there are 1,440 minutes in a day. And so when I do this, I can see, oh, look at this. I now have, based off of these start and stop times, I can manually find my duration of 8.76 minutes, which matches exactly what they were saying in STK. Okay, great. So I can recreate a number that I already have in front of me. How is that useful? Well, now I have all of those numbers actually right here where, okay, if this is 8 minutes, I could then say, all right, if my data rate is 2 gigabytes per minute, then I could then say the amount data added in gigabytes would be equal to whatever this value is times my 2 gigabytes. So now I can see that in that first contact, I've actually added 17.5 gigabytes. Now, you might be able to do this in STK. There's a bunch of cool things that you can do, but one of the things that we want you to get used to is actually being able to work with a spreadsheet, because those can be a lot more versatile and work with quite a few different programs. All you need to be able to do is bring the data in. There's actually a bunch of programs that are already programmed with the ability to export CSVs, the file types that we're looking at here. Okay, one thing that I'm going to put in here, I want it when I drag this down to stay on my data rate over here of 2 gigabytes. I'm going to do a trick in here. I'm going to do this quickly. It's referenced in other videos, but putting in dollar signs makes it where it will no longer move that cell. So here's what I can do. I taught it to do a thing. Now I'm going to grab the little circle on the bottom right and drag down, and that says take whatever math I've taught you and apply it to all the cells. So here's my duration in days, and here are all of my durations in minutes. And we can see that this is equal to this, so it's giving me exactly what I want. But now, what I couldn't get before is I drag this one down, and I now know exactly how much data I'm adding in each and every step. One of the other things that you could do, even if you don't want to do a thorough analysis of this, now that you've got these with your duration column, instead of just relying on the minimum, the maximum, and the average, you could also find things like the median value, the standard deviation, and you could go through, and if you're familiar with some of the statistics, you might be able to use something a little bit better than just the average on it. Okay, that's a little bit on working with these spreadsheets here. You can do this with a bunch of things. In fact, almost all reports in STK look for the little disk that has the green X in the background, and that's your save as a .csv. You can export all of the reports, at least all the ones that we usually use from STK, so that you can actually do a more in-depth analysis, which we'll talk about again in just a few minutes when we get to the lighting times and the power budget. One other thing that I could say is this is the contact with one location. I could also export the contacts for a second location, if I had one, into a CSV, and I could bring it into this file or into this page as well, and then I could actually do a sort and filter, which I believe is up here, create a filter. I can sort these where I would have it where they actually do a start and stop, or they organize each of these based on chronological order, which one happens when. That's where you can add things where, okay, this is where I'm adding data. When I bring in the other list, I could mark it that it's removing data, and then I can sort and filter them such that it puts them in order so I can see what happens when. When do I add data, and when do I remove that data? That's a way that you can go through and actually get a very good solution, but it takes a lot of work and can be very challenging. One other thing that I want to bring up is this. If you didn't know how to do this, we can also find our gap time. In other words, the time that we are not in contact. And I'm going to mark this in minutes. Okay, this one's going to get a little bit trickier. I'm going to go through, and to find my gap time, what I actually need is the time between my start point for one of them minus my end point from the previous one. And I'm going to put parentheses around this. That comes out in days. I can save a step and just say times 1,440. I can now see that after the first contact ends, and I got 8.8 minutes worth of contact time, my next contact happens sometime later and I get 13 minutes, but I now know that my gap is actually 89 minutes. So after the first contact ends, 89 minutes later, I come in contact again. I can now drag this down, and I now know more information than I did before. I know not only when I'm in contact and for how long, I now know how long is happening between each of those contacts. I could go through and find my average, my standard deviation, my median, all of those based on these numbers. Now, that can be very useful in general, but it's actually something that is programmed into STK. So to save you some time, I can show you this, but it's not something that is obvious. Like here, we've just got the access reports. When you're in the access menu, go down to Report and Graph Manager. Now there's a whole bunch of reports in here, but the one we're looking for is called gaps. I'm going to click on that. In fact, you can double click on it or click Generate. And we can see that our first gap, this actually does exactly what I just showed you how to do. Our first gap is 89.266 minutes. Well, let's double check what I found. 89.266. My second contact or gap between contacts is 90.1738, 90.174, which is 38 rounded to that. So there are two places that you can get the gap report. That can be very useful to see how long you are in contact and how long you are out of contact. Depending on what they ask you to do, both of those numbers might be very useful. I've now shown you several ways to access those. All right, that's what I wanted to go over for access times, and it also showed us how to work with CSVs. Let's go back over to our presentation, and we'll move on to the next phase. We're going to talk about Attitude Control Systems, ACS. Key ideas on this are satellites in space. One of the things that confuses people about space is it's so different from what we experience. I want you to imagine that you're sitting at a computer desk looking at your computer in one of those little wheelie chairs that you can kind of spin around in. And then you hear someone come in, like knock at your door behind you, and you want to turn around to look at that door. Well, in order to do that, you either have to reach out to your desk and push on your desk so that you can twist your chair around, or you need to put your feet down on the ground and actually use your feet to push on the ground to twist you around. Satellites have to do the same thing to point at whatever they want to look at, but they don't have any tables or ground to push off of. They're just floating out in space. Now, you may have some experience where you could kind of wiggle and shift back and forth and slowly tilt yourself, but that's actually interacting with things like a little bit of the ground through the chair, and then also like air. If you're out in space, you wouldn't be able to do that pretty much at all. So one thing that people don't realize, because space is so different from what we're used to, is it's actually kind of hard to change where you're looking at in space because you don't have the table or the ground to push off of. Attitude control systems are set up where that's what their job is. They're to allow a satellite to twist and look at different things. Now, common ones that are usually used with satellites are ones that use something called reaction wheels. Those are spinny things like gyroscope type systems inside the satellite that use a fancy principle of physics called conservation of angular momentum to allow themselves to turn without having to push off of anything outside of the satellite, because there really isn't anything. And also, more importantly, not have to burn any fuel or have anything like thrusters, which would require us to like shoot a puff of gas or something like that. Like little rocket engines. The problem with thrusters or little rocket engines are they need fuel. Now the reaction wheels are great, but sometimes you need something that's a little bit more precise than those. So some of the most advanced attitude control systems will have little thrusters, little like rocket engines you could imagine, not actually like all fire and brimstone and all of that, but they'll actually do like small releases of thrusters, little bursts of fuel that allow it to kind of point the way that it needs to. But the downside on this is it needs fuel, which means you're going to have to load up all the fuel that the thing will need for its entire mission as you launch the satellite, because there aren't really any gas stations up in orbit. So we have to give it everything that it needs. Without going into a whole bunch of detail on this, this is something that we see on a regular basis. A lot of times you will only look at a mission for, say, a 2-week period, but we very rarely put satellites, especially big satellites, up into orbit just to use them for a couple of weeks. We usually want them to stick around for quite a while, at least several years. And so as a result, if we want them to be able to point at what we need them to reliably for years, we may have to put a lot of fuel in there. Now, one of the most common problems that we see on this is keeping track of, hey, for long-term missions that might take several years, most people will immediately say that there are 365 days in a year. That's not actually quite right. Every 4 years, you have a leap year with 1 extra day. So, if your mission is more than 4 years, or even has a leap year in it somewhere, to account for that extra day, you need to make certain that you, account for that. The simplest way is to take the average number of quote-unquote days in a year, which would be 365.25. Basically say that you have an extra quarter of a day in every year, so that every 4 years you're going to end up with 1 more day. That'll work out pretty well for us to actually predict how much that we would need to make certain that we've got enough fuel for it. So, if you are looking for a long-term mission, and you are being told that, hey, your attitude control systems require, let's go to the next page here. If the satellite, the mission that we want is supposed to last 6 years, and the ACS that's needed for the mission, let's say one of the ACSs uses about 0.02 kilograms of hydrazine, kind of like rocket fuel, every day in order to stabilize the satellite. Well, for 6 years, we would have 0.02 kilograms per day times 365.25 days per year times 6 years in the mission, and we would end up with needing 43.83 kilograms of hydrazine for the entire mission period. Let's say we have a different ACS that's actually much better and therefore gets us better results and hopefully more points, but it comes at the expense of needing even more fuel. So we would have to load up, if it uses 0.028 kilograms every day, when we calculate that up doing the same thing, we would need instead 61.3 or almost 61.4 kilograms. Well, that's a difference of almost 20 kilograms. That's a lot to put into orbit. And our launch vehicle may not actually be able to take that added weight. Here's where you have to do design. While it might be best to try and get the biggest or the best attitude control system that you can, if you don't have enough fuel for it, then it might be better to go with one that doesn't do quite as good of a job, but can have enough fuel to continue doing that job for the full 6 years that we need. A key thing on this, and for many of the others that we'll see, pay close attention to your units. And when you're doing a set of multiplications and conversions like this, we call them related rates, make certain that you're setting up where you get things to cancel out. We have 0.02 kilograms divided by day. I multiply it by the number of days in a year, 365.25. My days will cancel out. And then I have kilogram per year, whatever that number is. But then I've set up so my years cancel out for 6 years. And then I end up with kilograms per mission. And that's where I get the total number of kilograms for the mission. Okay, that also applies to some of the others we look at. I wanted to point out, if you're getting overwhelmed by the numbers, look at the units. They'll help you figure out how you need to string those numbers together. All right, next up, power systems. Power systems, we have a few things to talk about. I was honestly a little surprised that we hadn't seen some power systems in the last set that we looked at, but it's a good thing for us to have to manage. Satellites are going to need a lot of electrical power to run their systems, especially if they have big, powerful computers, heavy transmitters, and powerful computers that actually process all that data. Some spacecraft can be set up with nuclear reactors, but that's usually few and far between. We really only do that if we're sending those far off away from Earth, never to come back. It's unlikely that we're going to put nuclear-powered spacecraft up into orbit to hang around Earth for a bunch of reasons. Therefore, most spacecraft are going to get their power from solar panels, which you may have seen quite a bit of. In fact, they're becoming more and more common in day-to-day applications. When I'm driving to work, I actually notice that there are a bunch of them on the tops of roofs these days for different houses. So solar panels are becoming a, bigger thing. The panels collect sunlight and convert it into electrical power. We're not going to go into the details of photovoltaics because we're already going to have a very long video anyway, but you're welcome to do some additional research on that. But the power that you can get from these panels is going to be dependent on 4 main things for our spacecraft. 1, the amount of light energy where the spacecraft is. That's called the solar irradiance. We're going to look at that in just a moment. 2, the solar panel efficiency. In other words, how good the panel is at collecting that light and turning it into electrical power. That's actually going to depend on the nature of the solar panel, how it's made, and out of what it is made. 3, the size of the panel. So small panel will give you a little bit of power, but if you get big solar panels or many solar panels, it can collect more light, which can get you more power. And then finally, for our spacecraft, the amount of time in sunlight. The solar panels will only generate electrical power when they're in sunlight. Okay, so the first thing, 1, solar energy, also known as solar irradiance. The first factor, it basically estimates how much energy the light around you has. One thing that I want to emphasize on this is, okay, around Earth, there's a pretty reliable value that we could at least quote, but you may be designing a system around, say, Mars or Jupiter or out by Saturn. And as you get farther away from the sun gets dimmer, which means we end up with less light in a given area, is the simple way of looking at it. We describe how much light energy there is for a given area, usually per square meter, with something called the solar irradiance. It's like a lamp. If you put your eye right up next to the light bulb, it's super bright. Don't do that, because it'll probably damage your eye. It's got so much energy, it can actually do that. But if you look at the same lamp from across the room, it may be bright, but it's probably not going to burn your eye out. And if you look at that lamp from down the street, it might seem very dim. Light spreads out, and as a result, it kind of gets dimmer the farther it has to go. So the solar irradiance, how much energy you can get from the sunlight, is going to change depending on if you're by Earth, or if you're by Mercury, or if you're out by Neptune. And we keep track of that with a value called the solar irradiance. The value near the Earth is about 1,300 joules per square meter per second, or what we would actually say is about 1,300 watts per square meter. Now that's under ideal circumstances, and if you could absorb all wavelengths of light and convert it into electrical energy. Which brings us to the second part, panel efficiency. Now the way the panels are built, and more importantly, out of what they are built, the chemical properties and the nature of the photovoltaics will affect how much of that light they can actually absorb and effectively turn into electrical power. We represent this with efficiencies. So we're probably not going to have solar panels with 100% efficiency or even close to that. So we won't be able to turn all the light energy into useful electrical energy. Now remember, with a percentage, 100% could also be written as a number as 1.0. 60%, as we see in my example here, could be written as 0.6. And so my examples I have are, if we had a solar panel that had 100% efficiency near Earth, and we had 1 square meter of solar panel, then we would have 100% efficiency times 1,300 watts per square meter times 1 square meter gives us 1,300 watts is what that solar panel would generate. If you had 2 square meters, then we would end up with 2 square meters times that, which would be 2,600 watts. So we'll get to that in just a moment, but that's panel size. If we were dealing with 60% efficiency, well, that's the same thing as saying 0.6 times 1,300 times 1 square meter, and we would get that that solar panel would generate 780 watts. Here's how you can do the first step in finding how much energy your solar panels will generate per square meter at a given location based on their efficiency. Next up is the panel size. Well, that's a way to find out for every square meter how much power we have. Now we could multiply that by, if we had 3 square meters, then we'd multiply it by 3. Now normally you're not actually doing it that way. A lot of times what you're going to find is my spacecraft needs, for example, 5,200 watts of power in order to keep it running. If the solar irradiance where I'm at is 1,200 watts per square meter, and the efficiency of my panel is 42%, and take a moment on this because I've seen students where they don't know exactly what to do with the percentage because it doesn't have units. Think about this. Your solar panel can only get 42% of what the solar irradiance is. In other words, how much energy is available from the sunlight, which is 1,200. So I would take 1,200 times 42%, or 1,200 times 0.42, which gives me 504. There's a logic check you can do on this. Since your efficiency is probably going to be less than 100%, your end number should be less than what the solar value is. You can't get all of the sunlight and convert all of it to electricity, unfortunately. But with this, if we know that we need 5,200 watts and the local solar irradiance is 1,200 watts per square meter, and my efficiency is 42%, I can string those together and I could find that while I only get 504 watts per square meter based on my efficiency and the local solar irradiance, so for every square meter I would get 504 watts, I need 5,200 watts. Look at this again. Set it up so your watts cancel out and we're left with meters squared. I can see that for this circumstance, I would need 10.32 square meters of panels. Okay, last thing is going to be the lighting times. Remember, all that's great about the solar panels, but they can only give you power when they're in sunlight, which brings us to one of the other things in STK to take a look at. Okay, so I'm going to come over to my satellite, and if I need to keep track of its power to make certain that it's getting plenty of it, and I'm using solar panels to recharge it, that means I need to know when my satellite is in the sunlight versus not. So I'm going to go over to my satellite, I'm going to right-click, and I'm going to go down to Reports and Graph Manager. Then I'm going to go over to the installed types, and I'm looking for lighting times. I'm going to take the report, generate, and I've got a report here that says, hey, my lighting times, sunlight times. This tells me every time my satellite is in sunlight, and I can see on my first contact with the sun, it's in the sun for about 51 minutes. It would probably be about 61 minutes, but that's at the beginning of the scenario, so it was in sunlight for 10 minutes before the scenario began. But I can see that I'm in sunlight for about 61 minutes, and then as you keep going, it may drop below. It goes a little bit less than 61. It goes down to 60.99. When I go all the way down to the bottom of the list, it drops down just a little bit more, but for the most part, we're seeing almost 61 minutes every single time. The last one's 50 minutes, but it's cut short because our scenario ends. And so our average is going to be about 60.8 it has there. And so pretty much every contact would be about 61 minutes in the daylight. Okay, great. So if I'm getting 504 watts every time, or every minute that I'm in, or the entire time I'm in daylight, in sunlight, then I can get an idea of exactly how much power I'm generating. However, we keep going down. We're not always in sunlight. We have penumbra times. Now, penumbra is when you're in partial sunlight. For a satellite, it's when you're cutting across the shadow of the Earth, where you're partway in the shadow of the Earth versus not. I'm not going to go into huge details on that, but your penumbra is probably going to be very, very small values, small enough that you could mostly ignore them. The big one that you're actually looking for is this, umbra times. Umbra is when you're in complete darkness. We can see here that while I have, on average, for every one of my orbits, I've got about 61 minutes in the sun, I end up with about 35 minutes in darkness. Now here's the problem. If you need, let's see, and I've got it here, if your satellite needs 4,800 watts of power at all times, and your panels generate 4,800 watts, then everything's fine so long as your satellite is always in sunlight. But as we just saw, it's very common for our satellite to go into the shadow of something each orbit, so you may have to add more solar panels so that you get maybe 5,200 watts of power when you're in the sunlight, and that gives you extra that you can charge up a battery. It's common for you to have to choose a battery as well as the solar panels, and the battery will keep your satellite powered when it goes through the dark. Then, as long as it has enough power in the battery to make it through the dark times, once you get back into the sunlight, if you've got enough, you can draw in power and begin recharging that battery. But you may have to do some math to make certain that you can fully recharge that battery. You'll need to do that with the lighting times report that we ended up showing. Oh, by the way, on the lighting times report, like most of the reports, up here, there's an export as CSV. So once again, you can put it in a spreadsheet to be able to do some extra math on it. Okay. Next up, one final note on this, on batteries. Have you ever noticed that as you use your cell phone over, say, the course of a year, the battery just doesn't seem as good as when you first got it? That's actually something that happens to pretty much all, well, equipment in general, but especially batteries. They have kind of a battery lifetime. And we usually keep track of that in cycles. And basically what that means is every time you charge and discharge your battery for a bunch of reasons that we're not going to go into, they become not as good and slightly less, let's just go slightly less good. Eventually, if you keep using them, the battery may get real bad and not be reliable anymore. Now, this is just something that happens with all equipment, and batteries included. Many of the ones that you might be looking at for these long missions, like 6 or 8 years, you may be choosing from batteries that not only have an amount of energy that they can store, but they also will warn you about their life cycles. You might have a battery that will last 10,000 cycles. You might have one that lasts 20,000 cycles. It's something that the manufacturer actually sends us where they say, basically, we guarantee that this battery can be charged and recharged and then discharged so it can power your satellite or whatever device you want, and that you can recharge it and use it, then recharge it and use it. And you can do that at least 10,000 times without it dropping below 90% of its original efficiency. In other words, pretty good battery. But it's a way of keeping track of how long you can actually use those batteries for. When it comes to the satellite equipment, well, these are measured in charging and discharging cycles, so that's going to be based on, hey, the times that we just looked at. 61 minutes in light, that's charging. Then we have 35 minutes in the dark, that's discharging, and then we come back to the light. So every time you go from light to dark, that's going to be a cycle. Now remember, we may only be looking at a 2-week period where there may be, 40 or 50 cycles, but you may also have to choose a battery so that it continues working for 6 years. So you might look at that time and see how that carries over to several years worth of mission time. Okay, last thing, that was the last thing for the power systems. Thermal management. I'm going to go a little bit quicker on this. If you get the chance, check out ISAT QR2 A series. The third scenario, which was Mars or bust, in the mission briefing, I actually talk a little bit more about some of the thermal management. One of the big things that surprises people is this. Space is cold, that's a true statement, but if you go up to space, your problem isn't so much that you'll freeze to death or have issues with freezing, because what you're thinking of, what most people are used to, is having the atmosphere around you where cold air will take energy off of you. Out in space, while it is very cold technically, you're not actually touching anything. So you're actually in the middle of a giant thermos, like a Yeti cup, except the best Yeti cup in the world. Your problem is not so much that you'll freeze to death, it's actually, especially for your satellite, that you'll cook it to death. If you leave your cell phone running for a significant amount of time, it starts heating up. Using that electrical energy, because of some physics stuff, causes it to heat up, and you end up with some waste heat, some energy there. And if you don't have any way to get rid of it, it's like sitting out on a summer day in really thick, heavy coats, or even a winter day for that matter. If you've got too many coats on, you might start to overheat even if surrounding you is relatively cold. So we've got to get that heat away from the satellite before it cooks it. The way that you would do that is with radiators. Now going through there, most likely your heat management is going to depend on how much power you're consuming, because remember, a good source of heat there is how much power you're actually using. If you're not using your cell phone very much, it's probably not going to heat up. But if you're having it do a bunch of things, watching video and listening to music and all that, then it's pulling a lot of energy from your battery and it starts heating up quite a bit. So you may have it where the heat you have to manage is based off of how much power your satellite actually consumes. You may have to add radiators on there. They're kind of like solar panels where they're kind of big open panels, and what they end up doing is they allow us to take some of that thermal energy and send it off into space in the form of infrared radiation. It's basically heat vision stuff. I'm not going to go into a bunch of details on that, but in short, more radiators, bigger radiators, are also going, more space I should say, are going to allow you to emit more light out into space, more infrared radiation, taking more of that heat away from your satellite so that you can regulate it. You may have to go through and add some radiators. Now that's going to be expensive and add some weight onto your satellite. But it gives you an idea on what you could do. Take a look at that ISAT scenario. It's Mars or bust, and it's got a few more details on working with radiators. All right, finally, propulsion. To draw this to the end. You may have to add fuel onto the satellite for the ACS, as we talked about before, for the little thrusters. But another thing that is common is satellites usually need a little bit of fuel and some small engines to do what's called maneuvers. A lot of times they can be nudged out of their orbit from gravitational effects from, say, the moon or Jupiter or other spacecraft. Not as likely, but possible. Sometimes they get nudged a little bit. And so as a result, it's important for us to be able to nudge them back. So many satellites or spacecraft will have small thrusters on them that you can use to do what's called maneuvers. You actually not just spin them, but actually kind of nudge them a little bit, push them back into orbit. Sometimes we can even, to save on our launch vehicle, we have the rocket ship go up and go to what's called a parking orbit, say a low Earth orbit that isn't actually the orbit we want the satellite in, but is close, so that the rocket can actually let the satellite free there, get it set up in an orbit, and then fall away, and then the satellite will use fuel on board the satellite to actually move from its parking orbit to its permanent mission orbit. There are some reasons why that can be very useful, but it's something that you might have to keep an eye out for. If you do, well, that satellite, once again, has to carry that much fuel. So this is another place where you might be adding fuel to your satellite. If you have both an ACS that needs fuel and you need to do some maneuvers like transferring orbits, then you will need to add enough fuel to do those things. Keep track of, it's not just one source that you need fuel from. You will need the fuel for the ACS and its entire mission time, and you will need the fuel to do any of these maneuvers so that you can actually move the spacecraft, hence propulsion. Usually these propulsion-based ones are a one-time thing or very infrequent, as opposed to the ACS, which is kind of a constant, needs a small amount of fuel at a constant rate. So, things to keep an eye out for. This is a rundown of the main things that I can think of concerning the prep recommendations that we were given by StellarX. Once again, apologize for a long video, but hopefully you found this useful, and good luck. Tenye wachesh gut.